Hello, the purpose of this screencast is to show you how to do the Module 10 homework over Chapter 8 in the Graviter and Wallno Statistics book. So Chapter 8 covers hypothesis testing, and this homework assignment has a lot of questions about hypothesis testing. So in question 4, the first one on the assignment, it's asking you what happens to the critical region and the probability of a type 1 error when you change alpha level. So on the actual assignment itself, it's asking what happens when you change from 0.05 to 0.01. Obviously, I don't want to give you the answer exactly in this screencast, but I can walk you through if I change the problem slightly and instead of going down, increasing alpha to 0.10. So what would happen to the boundaries of the critical region? For this one, I'm going to look at one of the practice problem illustrations that you have seen. So I think it was practice problem 8.1, there was this question about critical region. And so here we have the normal bell curve, and we have it drawn so that this would represent the critical region for a two-tailed test, right? We have a tail up in the positive end and a tail down here in the negative end. And it would represent like at the 0.05 level. And it's saying that the region of rejection is here in these red boxes if we're testing at the 0.05 level. So we've got half of that, 0.025% of the population in this red block, and the other bottom half, 0.025% here. When we add those together, it's a 0.05 or 5% region of rejection. Now, what if I were to increase it to 0.10, meaning 10% region of rejection? Well, you can imagine that what we're doing is we're increasing it this way so that instead of only allowing this tiny portion of the tail, I'm extending it this way, and I can extend it that way as well. So what I have in effect done is extended the region of rejection or made it larger. Now, what happens to the probability of the type 1 error there? So type 1 error is when you say that you have an effect and you really don't. This is bad. For example, let's say I'm testing a new study method like making screencasts for a statistics class. And let's say that I say that these screencasts work and they're going to improve people's grades, but they don't. That would be a type 1 error. So I want to try to avoid those. Well, notice that if I keep my alpha low down here, I'm becoming more stringent, right? I have to have a bigger Z value in order to reject the null, right? But when I make it less stringent, I increase to a 10% risk. Now my Z can be lower, and I can say that I have an effect when I really don't. So if I increase alpha from a 5% risk to a 10% risk, then the probability of my type 1 error is going to increase. If I become more stringent, then my probability would decrease. Okay, so that is a walk through problem 4. How about problem 8? So problem 8 asks about testing a hypothesis. So it's giving us this hypothesis here about childhood participation in sports. It's telling us that a representative sample has been drawn of 100 adolescents who have a history group participation, and they take this self-esteem questionnaire. We want to compare the results of their questionnaire to the general population of adolescents who have a mean score of 50 on the test with a standard deviation of 15. Our sample had a mean score of 53.8. So that's the information given to us in the problem. We're dealing with a population mean of 50, comparing it to the sample mean of 53.8, and the standard deviation in the population is 15. Now we want to test the hypothesis that our sample is significantly different from the population, and the problem is telling us that we want to do a two-tailed test with alpha set at 0.05, or a 5% risk that we make a type 1 error. Okay, so it's asking us to identify the two hypotheses, determine the critical region, compute the test statistic, and use that test statistic to make a decision. How do we do that? So the first thing we need to do is state the hypotheses. So remember, the two hypotheses are HO and H1, right? HO is the null hypothesis, and it's always testing that you don't have an effect. That is, that the means are equal or not different. And then the alternative hypothesis is going to change depending on if you have a one-tailed or two-tailed test. This is a two-tailed test, so we're just testing that the means are equal. And so then H1 is going to be that the means are not equal. And you can see examples of these in practice problems 8.1, 8.2, and 8.3. So the critical region, or the region of rejection for a z-test, is always the same. How you find the critical region is you look up your alpha value in the tails on the z-table. And so we can see in some practice problems how that was done. So for example, you look up this is a different problem, but you have this proportion in C, and you look up for your value that you're testing. For alpha equals 0.05, you would look up 0.0025. And we have done this in previous problems. And so we already learned that the actual value for that is 1.96. So the critical region for a two-tailed test where alpha equals 0.05, the critical region is plus or minus 1.96. What that means is that if your obtained Z value, and we represent that with the Z subscript OBT for Z obtained, that means the value that you're going to calculate with the z-test formula. If that Z obtained value is greater than the critical Z value, represented by Z crit, which we determined to be plus or minus 1.96 for this problem, a two-tailed test with alpha set at 0.05, then we can reject the null and say that we have a significant effect. So I'll say that again. If our obtained Z, or the one that we calculate in this problem, is bigger than plus or minus 1.96, and remember to be bigger than the negative 1.96, it could be negative 1.97, negative. It works the same way as the positive. You're just going beyond that value on the normal bell curve, then we reject the null. Helpful tip, Z crit for a one-tailed or directional test where alpha is set at 0.05 is plus or minus 1.65. We'll see that in a later problem. So once you understand that, what the critical region is and what they mean by Z obtained versus Z crit to make your decision, it becomes really easy. All you have to do is plug in the numbers that you were provided into the formula and do the calculations. So the formula for Z to compare the sample to a population, right, our sample of 100 versus the population mean of 50, is to plug in the mean for the sample, which was 53.8, minus the mean of the population, which was 50, divided by the standard error of the mean, where you calculate that by dividing standard deviation by square root of n. So in this problem, it'd be 15 divided by 10. So you do that math and you get Z obtained, a value. Then you compare that value to 1.96. If it's greater than 1.96, you can reject the null. Your scores are significantly different. They are not equal, is what your null is saying. Okay, so that's how to do Z. Now, what about this Cohen's D? So Cohen's D has another formula. Here we are dividing the means by the standard deviation. You just follow the formula, plug in 53.8 minus 50 divided by 15. You get a value, and then you use these guidelines from this practice problems to interpret that. So if D is equal to 0.02 or less, you have a small effect size. If D is equal to 0.5 or less, you have a medium effect size. If D is greater than 0.8, then you have a large effect size. Okay, for problem 14, it's the exact same problem. You're comparing a sample to a population. You're given the population mean, you're given the sample mean, you're given the sample size, and you're given the standard deviation of the population. Use the same formulas and then just critically think about, let's see, if I'm doing a two-tailed test and now alpha is set at 0.01, here's the difference. It's still a two-tailed test, so your hypothesis is set up the same. The null is that the means are equal. The alternative is that they're not equal. Here we just use a different z critical value because we're setting alpha at 0.01 instead of 0.05. So this was exactly one of the practice problems in practice problem 8.3, where we had to look up, since we're setting it at 0.01 in a two-tailed test, we have to look up half of that, 0.005 on the z-table in the proportion in the tail to find that z-score. So we go to the proportion in the tail, we find 0.0049 and 0.0051. 0.005 is exactly equidistant. The z-crit for the two-tailed test then would be plus or minus 2.575, or I just round up to plus or minus 2.58. Okay, so then you calculate your z obtained and compare it to the 2.58. If it's greater than, you reject. If it's not greater than, you don't reject the null. And then you solve for d. Let's see, in this one, yes, you make your decision and then you solve d and interpret that effect size. Okay, next problem, same thing. We are comparing a sample to a population. The difference here is they're asking for a one-tailed test with alpha set at 0.05. Since it's a one-tailed test, we can use the table and just look up 0.05 in the tails, right? So question 16 is similar to the other two above, only now it's asking you to conduct a one-tailed test with alpha equal 0.05. Sorry, one tail point, just look up 0.05 in the tail to get z-crit or memorize it, it's plus or minus 1.65. Also make sure that you set up your hypotheses as one-tailed tests now. Here you use the little alligators to indicate greater than or less than, and practice problem 8.2 can show you how to do that. Okay. Problem 22 is the last one on the assignment, and here it's asking you to think about how sample size influences each of the following. Here's my tip for you. For A and B, it's asking you how size of Z affects your Z-score in a hypothesis test, and also Cohen's D. To answer these kinds of questions, think about how sample size factors into each of your formulas. If n isn't included in the formula, then sample size doesn't matter. However, if n is included in the denominator, that means the bottom of the formula, the larger the n, the greater the score. And let me show you how. First, let's refresh our memory on the formulas. So z, it's hard to see here, right? The z proper is just the mean minus the mean of the sample minus the mean of the population divided by standard error of the mean. But remember, standard error of the mean is taking the standard deviation divided by the square root of n. That's going to be important here, and let me show you how why. D, notice there is no n anywhere in there. Okay, so why? Why does that n square root of n matter? So let's say we have a sample of 10 people versus a sample of 100. The z-test formula requires that we take the square root of n to solve, right, to get that standard error of the mean, and then we divide standard deviation by that. So let's compare the sample sizes of 10 and 100 in a distribution where the standard deviation is 15. The square root of 10 would be 3.16, and the square root of 100 would be 10. So if I'm calculating, and this would be the standard error of the mean, right, that O sub m, would equal the standard deviation 15 divided by the square root of n. And here, if my square root of n in a sample of 10 is 3.16, my standard error of the mean is 4.75. And then here, my standard error of the mean is going to equal 15 divided by 10, or 1.5. So then these numbers are going to go into the denominator, the bottom of that z-test formula. So let's say we're comparing mean differences of 5, right? Let's say I had 105 in the sample and the mean in the population is 100. So now my z, I have 5 divided by 4.75 if my sample size was 10, and it gives me a z-score of 1.05. But if my sample size was 100, my when I'm dividing my denominator by standard error, the mean is 1.5, and now my z-score is 3.33, way out beyond the critical region, right? I mean, the biggest critical region we've seen so far is 2.58. So these bigger sample sizes yield bigger z-scores, and they're going to increase the likelihood you reject the null. If you reject the null, you risk a type 1 error, right? You're going to say, oh yeah, I have a significant effect here, even if you don't. And so testing larger sample sizes, yeah, it gives you the power to reject the null, but it might not be an accurate decision because it's increasing type 1 error. So think about that. Go back and review what it's explaining in the book, because I do think that that's helpful to answer about how sample size affects power and also type 1 and type 2 errors. But as always, if you have questions, just reach out and ask for help. The next part of this homework was the Excel, which you can watch in another screencast.